The calculation theta equals theta v minus theta I occurs really, really frequently in power systems. In fact, it occurs so frequently that we give it its own name, and we call that thing the power factor angle. Power factor angle. The cosine of that angle is called the power factor. Power factor equals cosine of theta. This is super common in power systems, to be given the power factor of a load, which is going to tell you the relative angle between voltage and current, but they don't say it this way. They give you a power factor. So they give you power factor, it's abbreviated PF, very common method for specifying whether a circuit is lagging or leading. We'll note that the value of the power factor doesn't actually tell you the value of the power factor angle, because cosine of theta v minus theta I would be equal to cosine of theta I minus theta v, because cosine of minus theta is equal to cosine of theta, right? You guys remember that from trig? So it actually doesn't tell you if it's lagging or leading. It just tells you what the relative phase shift is. So you'll hear terminology such as 0.85 power factor lagging or 0.7 power factor leading, and we'll investigate some of these ramifications. So to completely describe the angle, we have to use these terms lagging power factor and leading power factor. So to describe it completely, we say that lagging power factor means that current lags voltage. So whenever you hear that from now on, lagging power factor, current lags voltage, as in an inductive load. Leading power factor, the term leading power factor alternatively means that the current leads the voltage, is in a capacitive load. So if you ever hear someone say that it's a lagging power factor, we know that the current lags the voltage. That's an inductive circuit. And if someone says that the circuit has a leading power factor, we mean that the current leads the voltage. It's in a capacitive circuit. In both cases, we're referring to the relationship from current to voltage, right? Current. In a lagging system, current lags voltage. In a leading system, current leads voltage, right? We're always saying current first in the sentence and then voltage second, which makes it a little easier to remember. In other disciplines, like we said earlier, the peak phasor is often used in ECET. In power, recall that I mentioned that the RMS phasor is typically more useful. In fact, the use of that RMS phasor is so common that most of the time power engineers are simply assuming that voltages and currents have been stated in terms of their RMS values. And so will we in this class. So for the rest of the semester, unless otherwise explicitly stated, we're going to be performing our circuit analysis using the RMS values of voltages and currents. And now we're going to take some time to look at the use of the RMS value for power calculations. So we're going back to our original equations for instantaneous power. We have the instantaneous power at any time is Vm Im over 2 cosine of theta. Which is, remember, what we call the real portion. Then we've got a double frequency component of real power, and then a double frequency component of reactive power here. And these kind of look like zeros in here to me, and I want to make sure that you guys don't think that those are zeros. Something must have happened with the type font when it got converted over here. Those are thetas, right? That's Vm Im divided by 2 cosine of theta, not cosine of 0. So it looked a little off to me. So just remember that that's a theta, right? This being called the real portion, this being called the reactive portion, right? So we're going to make a simple substitution into this equation, and it's going to reveal something that I find kind of enlightening. We've got the power V max I max over 2 cosine of theta. Simple substitution is going to be, let's do V max over radical 2 times I max over radical 2 cosine of theta, right? Very simple substitution. What we can see is that the denominator of this equation, radical 2 times radical 2 is just going to be 2, so we haven't changed it. But what is max divided by radical 2? It's the RMS value. So this is just V RMS I RMS cosine of theta. I can make almost the exact, well, not almost, the exact same substitution for Q here. I could say, just clarify that, V max over radical 2 times I max over radical 2 sine of theta is going to just end up showing me that Q is equal to V RMS I RMS sine theta. So these manipulations, what did they show me? They showed me that P, the real power here, and Q, the reactive power, can easily be calculated using the RMS values. And since we use the RMS values, P and Q are going to represent the effective power or the average power delivered by the sinusoidal voltages or current sources. So therefore, instead of using the instantaneous power P of t equation, remember this gives us the instantaneous power at any time t, which is really only going to tell us information, which tells us specific information about power at some specific time t. More frequently, what we're more frequently interested in are what are P and what are Q, because they represent the time averaged behavior of the circuit that we're analyzing. So remember earlier we wrote out this big equation and I said this is the equation for instantaneous power. It's a big hairy equation. It gives us some ideas about how power works, but don't worry, we don't use it all that much. That's because in power systems we're mostly interested in time averaged quantities, right, over the period of one cycle. We want to know what the average behavior is over that one period of the AC cycle, and the quantities that represent that are P and Q. So these are what we end up using in power systems analysis. So we can make some further observations for specific circuit types. In a purely resistive circuit, the average power, P, is going to be, well, that's going to go to 0, so it's just going to be V RMS times I RMS, right? Because there is no phase shift in a purely resistive. This simply means that in the case of a purely resistive circuit, average power is just V RMS times I RMS. Just like we would have expected, the voltage times the current in a resistive case, right? Q, I RMS times V RMS, sine of 0, 0 VARs. There is no reactive power in a resistive circuit. Very interesting. So no reactive power is supplied to it from a resistor. Now what about an inductive load? Well, the average power here is going to be I RMS times V RMS times the cosine of the phase shift. We know that there's a 90-degree phase shift between the voltage and the current here. So theta V minus theta I is 90 degrees here. This term goes to 0. If I plug in a 90 here, sine of theta is 1. We get Q equals V RMS times I RMS. So we find that the Q is of a purely inductive circuit is just V RMS times I RMS VAR, right? Positive VAR. For capacitive load, cosine of negative 90 degrees, 0. No average power in a capacitor, right? Plug in negative 90 here, what do we get? Negative V RMS, negative I RMS. We get a negative VAR. So again, we see that positive Q results from an inductive load, indicating that the inductor is consuming VARs, and the negative Q we see that results when we put in a capacitor indicates that the capacitor is kind of supplying the VARs. So a lot of times, we indicate this in behavior by putting an average down here. The average power in an AC circuit is V RMS I RMS cosine of theta, where theta, remember, is the power factor angle, and then the reactive power measured in VARs is V RMS I RMS sine of theta. I say this a lot, I guess, maybe once a class. Equations worth memorizing, right? So these techniques can easily be extended to analyze circuits that contain both resistance and reactance, right? We don't have to have circuits that are just one or the other. Circuits that contain complex impedance can be analyzed using these techniques. So you're going to recall that in any load containing reactance, the relative timing of the voltage and current results in a phase shift so that the maximum of the voltage and the current don't coincide. And again, if we were interpreting this graph, we would need to recall that in a purely resistive case, the instantaneous power is completely positive, and in the capacitive and inductive case, instantaneous power is positive 50% of the time and negative 50% of the time. So their average power is 0, right? What about when the IV waveforms are out of phase by an amount that's between 90 and negative 90 degrees, right? It's complex impedance. Well, the real power is going to be I'll say this slowly. Real power will be decreased as compared to the resistive case, and the reactive power will be decreased as compared to the purely reactive case. The reduction is accounted for mathematically by the inclusion of those cosine and sine terms, right? So we see that the average power, P average, is equal to I RMS V RMS cosine of theta. So what does that cosine of theta term do in cases that aren't 90, aren't negative 90, aren't 0? What if it's like 45 or something like that? Remember, cosine oscillates between negative 1 and 1. So what it does is it will, the phase shift, and remember phase shift is constant in the circuit, so that cosine of theta term is going to reduce that, right? It's going to make it something smaller than the power that would have resulted in a purely reactive or a purely resistive circuit, right? Purely resistive circuit, IRMS, VRMS. What's the influence of the reactive portion? Well, I find out what the phase shift is, and it reduces real power. Q average, similarly, remember just from that last slide, IRMS, VRMS. This time, though, it's sine of theta. Theta, again, is going to be the phase shift. If it was a resistive waveform or resistive load, that's 0. Sine of 0 is 0, so there's no reactive power. If it's an inductor or capacitor, it's going to be 90 and negative 90 respectively, which means that's going to be 1 and negative 1 respectively. These things are going to be at their maximum value, right? If this was some other value, all it's going to do is reduce this down from IRMS, VRMS, maybe times 0.5 or something like that. So these equations here are always true and work for any kind of load and are probably the equations most frequently used in this course, right? Memorize them. I gave them 2 slides just to tell you to memorize them. They're that important, right? So let's do a quick example of the use of RMS for power calculations. We've got an AC voltage here with a max amplitude of 625 volts, and we're going to apply it to the terminals of a 500 ohm resistor. Find the average power in the resistor. So we're going to take the voltage, we're going to use it as the reference phasor. We want the voltage phasor, there's a capital V. Remember, we need to use RMS. We were given peak, so we need to do 625 volts. We need to divide that by square root of 2. That converts it to RMS. We use it as the reference phasor, which means it's at an angle of 0 degrees volts. So what does that give us? We do the math there. It's 441.94 degrees at an angle 0 degrees. From Ohm's law for impedance, we then go to I equals V over Z, and we get 441.94 at an angle of 0 degrees. And what was this? Well, this was a resistor, 50 plus J0 ohms, and that's going to give us 8.84 amps at an angle of 0 degrees. We can then calculate average power. The average power consumed in the circuit is I RMS times VRMS times the cosine of the angle, so that's going to be 8.84, that's the RMS value, 4.41.94, and then cosine of the phase difference, so the cosine of 0 minus 0, so that's going to be 441.94 times 8.84. Cosine is 0 minus 0. And that gives us 3,906.75 watts. All right.